everyone, I'm Boyuan Liu. I'm a senior student with double major in physics and astronomy at UMass Amherst. My advisor is Professor Ming-Su Yun, and today I'm going to present about my honor thesis, searching for the most luminous galaxies in the universe. And here's an overview of today's talk. Before I get into the research, I want to give some background about my research. So, in the 1980s, a new class of galaxies was discovered. It is infrared galaxies, and such galaxies emit more energy in infrared wavelength. And in this kind of targets, there are some really bright objects. It's called infrared luminous galaxies, or LURGs in short. The enormous infrared emission is caused by the merger of gas-rich spirals and the heated dust from the starburst within the molecular cloud, and the gas funneled into the center of the merger funnels fuels the interaction. However, in the early universe, the average gas density is higher than that in the local universe, and another type of galaxies known as submillimeter galaxies with extremely high star formation rate have no counterpart in the local universe. And this implies an unknown process of gas inflow. And in order to investigate this mystery, the very first task is to find a laboratory of galaxies with extremely high luminosity in the high redshift region, because efficient gas accretion is needed to support this kind of high luminosity. And here are two plots in the slide. They are SEDs of these kind of galaxies. And the left-hand side is the SED of dusty star forming galaxy in the rest frame, and the right-hand side shows the SEDs of dusty star forming galaxies in different redshift regions from z equals to 1 and to z equals to 5. And these two plots are all cited from Berman's paper. So I want to focus on the SED on the left-hand side. And you can see there's a peak around 10 microns. And this is the hot dust emission. And this hot dust is surrounding an AGN and will absorb the high energy photons and re-emitted them in the infrared range. And this bigger peak is the cold dust emission. The cold dust will absorb like UV and optical photons from the stars and re-emitted them in a longer wavelength. And these two peaks could be described using the modified blackbody radiation. And this line here is the synchrotron radiation in the radio wavelength. And after a critical frequency, it will start to drop really fast. And in the previous study, there are 22 dusty stars forming galaxies are found from Planck's catalog of compact sources. And these 22 targets are found using the wideband photometry, actually the W1 and W2 color magnitude diagram. Well, this plot is also cited from Berman's paper, and it shows the result of the CMD of W1 and W2 color magnitude diagram. So overall, the disadvantage of this kind of method is they only use two pieces of information of wideband, and also they will lose 20% of about 20% of the targets in the data set. So in my research, I'm trying to use another approach, a statistical approach, to find a better statistical sample and the best possible targets for the follow-up investigation. The way I did it is using principal component analysis, or PCA in short. Well, PCA is a widely used statistical method in a lot of fields. So for example, in computer science, in data science, in finance, and of course in physics and astronomy. And the idea of PCA is it will find a direction that carries most of the variance of the data set, as you see in the plot on the right hand side. These two vectors are the principal components, while the the first principal component here carries most of the variance of the data set. Then if we project our data onto PC1, we can reduce the dimension of the data set and describe the data, use only one feature. And that is one of the main use of PCA, is to reduce the dimension of the data set. And here is the math derivation of principal component analysis. We use the matrix transpose multiplied by the matrix itself to calculate its covariance matrix, and the principal components are the eigenvectors of this covariance matrix. And here's an example of use of PCA in astronomy. Well, this plot is cited from the paper I list below. And in this paper, they study over 16,000 quasars in SDSS, and they use PCA to analyze their spectrum. The plot here lists the first 4 eigenspectrum they derived using PCA. And the first 4 spectrum count for about 22% of the total variance of their data set. And the first eigenspectrum means is the mean spectrum. And the second eigenspectrum is tell us about a host galaxy component, and the third spectrum is the UV optical continuum slope, and the fourth order eigenspectrum is the correlation of the Balmer emission lines, and more details could be found in the paper I listed below. And come back to my project. In order to test whether this method could work, we had 2 test data sets. Well, the first test data set consists of AGNs and dusty star forming galaxies. Well, there are about 50% of the targets are AGNs, and another 50% of targets are dusty star forming galaxies. So in this data set, the number of two class of objects, they balanced, and as you see, they are greatly separated in the PC1 versus PC2 eigenspace. And also there are 2 regions for AGNs, which tell us there might be 2 kinds of AGNs in the dataset, which is great. And then we go to the second test dataset. So on the right hand side, it shows the result from the second dataset, where the second dataset is closer to the real data, because in this dataset, over 70% of the targets are foreground galaxies, and about 20% of targets are AGNs, and only less than 10% of targets are SMGs. So this is the result after normalized the dataset. And as you see, there is a pretty clear line right here that separates the high redshift objects with the foreground galaxies, which is great. So go to the final step of this project. We want to select the high redshift objects from the PCCS. And then, as you see here, we already have a pretty great eigenvector space that can separate the foreground galaxies and the high redshift regions objects. So we can project all of our PCCS samples onto this eigenspace. Like in PCA, in the PCA eigenspace, if 2 targets have similar properties, they will be close together, so that we can say if the projection of a target in PCCS is higher than the line in the eigenspace, we can say that that is a high redshift targets. And on the other hand, if that falls into the region that lower than the line, it will be a foreground galaxies, and we will ignore that. And after I don't have a result yet, but after I have a candidate for the targets we need, I will compare the result with Jackie, and she's using the machine learning to find the targets in PCCS, and we will compare our result to see how much targets are overlapping. Thank you. And this is all the target, and this is all talks for today. Thank you very much for listening.